Percent composition allows you to calculate the simplest ratio among the atoms found in a compound. This simplest ratio is known as the empirical formula, or the lowest whole number ratio of atoms in a chemical compound. Molecular formula is the actual formula of the compound, showing the actual number of each element present in the chemical compound. For example, C4H10 is a molecular formula, while C2H5 is the empirical formula. C2H5 is the reduced form of the C4H10. Example number 2, C6H12O6 would be a molecular formula because it could be reduced down, while CH2O would be the empirical formula. Let's look at how we would calculate an empirical formula. In this example, we have an oxide of aluminum that is formed by the reaction of 4.151 grams of aluminum with 3.692 grams of oxygen. Our job is to calculate the empirical formula. First, let's determine the number of grams of each element that's present. That would be 4.151 grams of aluminum and 3.692 grams of oxygen. We need to convert from grams to moles. We take the 4.151 grams of aluminum. We will convert that to moles using our mole conversion of 1 mole equals the weight from the periodic table. So 26.98 is the weight from the periodic table. This allows grams to cancel out, leaving moles, and we would have 0.1539 moles of aluminum. Likewise, we need to convert 3.692 grams of oxygen to moles of oxygen. We know that 1 mole of oxygen weighs 16 grams, since 16 is the weight of oxygen from the periodic table. Again, grams cancels. We are left in moles, so we have 0.2308 moles of oxygen. Now, we need to find a ratio between our two elements in our chemical compound, aluminum and oxygen. We have calculated that 0.1539 moles of aluminum was present and 0.2308 moles of oxygen is present. We look at each of these numbers and we decide which number is the smallest. We divide each element by that smallest number. So 0.1539 is smaller than 0.2308. So we divide the moles of aluminum by itself and we get 1 mole of aluminum. Likewise, we divide the moles of oxygen by the moles of aluminum, which was the smallest number, and we get 1.5 moles of oxygen. Therefore, our ratio would be for every 1 aluminum, we have 1.5 moles of oxygen. However, we cannot write a formula with decimal points. We could not write AL1O 1.5. So we must multiply by a common factor to get the whole number. If we take our 1.5 and multiply it times 2, we would get the whole number 3. But just like in mathematical problems, whatever one does on one side of the equation, they must do on the other side of the equation. We must do the same thing with our elements. If we multiply oxygen by 2, we must therefore multiply aluminum by 2. So 1 mole of aluminum times 2, we get 2. Therefore, our chemical formula would be Al2O3. Now let's look at one more example of empirical formulas before we move on. In this example, we are given 4.55 grams of cobalt, and it reacts with 5.475 grams of chlorine to form a binary compound. So we will determine the empirical formula for this compound. The first thing we will do is we will convert our 4.55 grams of cobalt to moles of cobalt. We will use our conversion factor that 1 mole equals the weight from the periodic table, since 58.93 is the weight of cobalt. This allows our grams to cancel out, and we are now in moles of cobalt. Likewise, we will take 5.475 grams of chlorine, use our conversion factor of 1 mole equals the weight from the periodic table. So here we have the weight of chlorine from the table. This allows grams to cancel out. We are now in moles of chlorine. As we compare these two numbers, we will determine that cobalt has the smallest number. Therefore, we will divide each of these by the moles of cobalt. So cobalt divided by itself, we get 1. Chlorine, the 0.1544 divided by 0.07721, we get 2, resulting in our empirical formula of CoCl2. Let's look at one last example of empirical formula before we move on. Now, in this example, you are asked to calculate the empirical formula for lead arsenate. This would be a good time to pause the video, attempt to solve this problem on your own. The solution is on the next slide. If you have any difficulty, review over the beginning portion of this video or come into my classroom and get some additional assistance. Well, here is the solution to our lead arsenate problem, PbHAsO4. I hope you got the correct answer, and if you had any difficulty, please stop by my classroom and we will review one-on-one on where you still have some difficulty. Now, before we leave calculating empirical formulas, we do need to add one additional twist to this problem, and that's how can we use an empirical formula to calculate a molecular formula. It would be impossible to do this if the problem does not give you the molecular mass. So let's look at a few of these problems and how we can use empirical formula, molecular mass, to actually come up with the true formula of a chemical compound. This will be extremely useful in our upcoming units in chemistry. So in this empirical problem, we have a white powder that is analyzed and found to have an empirical formula of P2O5. The compound has a molecular mass of 283.88 grams. What is the compound's molecular formula? Well, in this particular example, a lot of the work has already been done for us. You see, we are given the empirical formula and we are given the molecular mass. So the first thing I would do is find the molar mass of our empirical formula. We have 2 phosphorus, each weighing 30.97 from the periodic table, total mass of 61.94. We have 5 oxygens, each weighing 16 from the periodic table, with a total mass of 80. We add these two numbers up and we get a molecular mass of 141.94. Our total mass of the chemical compound is 238.88. Remember, we received that from our original problem. So we will take this 238.88, we will divide it by 141.94, our molecular mass of our empirical formula. And we get the number 2. We take this 2 and we multiply it times our empirical formula. So 2 times 2 is 4, 2 times 5 is 10, and we get a molecular formula of P4O10. Let's look at one additional example of this problem. A compound has an experimental molar mass of 78 grams per mole. Its empirical formula is CH. What is its molecular formula? Well, the first thing we're going to do is we're going to come over and we are going to calculate the molecular mass of our chemical compound. We have one carbon weighing 12.01, one hydrogen weighing 1.01, total molecular mass 13.01. We take our mass that was stated in our problem as 78. We divide it by our molecular mass. We get the number 6. We multiply 6 times our empirical formula, which was CH, and we get the answer C6H6. It is that simple. Now, the only twist that can be added to these problems is if the empirical formula is not given. In this case, percentages or grams would be given, and you would work this problem, find the empirical formula just as you've done previously, and then you would begin at this point here by finding the molecular mass and dividing the total mass of the compound by the molecular mass. In this example, 2 grams of iron metal is heated and it reacts with oxygen to receive a final mass of 2.57 grams. Determine the molecular formula. The molecular mass is 216. In this equation, we know that we have 2 grams of iron. We take our 2.573 grams of iron, we subtract 2 from that, and we see that 0.573 grams of oxygen is present. We will now convert our grams to moles. So our 2 grams of iron, using our conversion factor of 1 mole equals the weight from the periodic table, cancels out our grams. We are now into moles for iron. We take our 0.573 grams of oxygen, using our conversion factor of 1 mole equals the mass from the periodic table, cancel out our units. We are now in moles of iron. We look at these numbers, and they are the same numbers, so we divide them by the smallest number. We get a 1-to-1 ratio, or an FeO. Now the next thing we would do is we would find the mass of FeO. Now the molecular mass of FeO is going to be 72. We take the molecular mass of 216, we divide it by our empirical mass of 72, we get 3. We take this 3 and we now multiply it times our empirical formula, resulting in our answer of Fe3O3.